Welcome back, everyone. So today we're going to be going over section 3-4 in your textbook, which talks about the rational root theorem. So before we start, I just want to let you know that this section of the chapter is pretty dense and has a lot of topics of critical import. So you may want to take it a little bit slowly. So before we get into the rational root theorem, I want to first start off by going over a few key points from the last lecture pertaining to the quadratic formula and the factor theorem. So just to reiterate, the quadratic formula is given by x equals negative b plus or minus the square root of b squared minus 4ac over 2a. Now, this is the be-all and end-all way of finding a solution for a quadratic. So this is the de facto way of finding all solutions of a quadratic. Now, it is important to know that this is the method of last resort. So just like you can take a car and go anywhere, you should determine when would be the best time to take a car, right? Like, for example, if you would just go to your neighbor's yard, you're not going to go into your car, drive out of your driveway just to go right one house down up their driveway in a car. You just walk across the yard. So the same thing with the quadratic formula. You don't want to use the quadratic formula to solve all types of quadratics. You only want to use the quadratic formula when you cannot solve the quadratic via factoring. So remember how we solve quadratics. We have to have one side equal to 0. So we move everything to one side of the equation and have the other side equal 0, and then we try to factor. If factoring doesn't work, that's when we can use the quadratic formula. Now, it is pretty involved. There's a lot of numbers, and the equation is kind of messy. But remember, if you break it up into pieces, then it's a little bit easier to use. Now, the first thing we have to emphasize is that the a, b, and c in the quadratic formula come from the coefficients of the quadratic equation in standard form. So a is your leading coefficient, b is the coefficient of your x variable, and c is your constant term of the equation written in standard form, ax squared plus bx plus c. Now, when we're working with a quadratic, it is always important to go ahead and first calculate your discriminant. The discriminant is the b squared minus 4ac, the stuff that's underneath the radical sign in the quadratic formula. And the reason the discriminant is valuable is because, as we talked about in the last lecture, it tells you the characteristics of your solution. It doesn't tell you the solution, it tells you what type of solution you expect. Now, the discriminant is a number, so it either can be less than 0 or negative. It can be equal to 0 or it can be greater than 0. If the discriminant is less than 0, that means it's a negative. That means you should expect two imaginary solutions. That doesn't mean what you calculate for the discriminant is those solutions. It says that if the discriminant is negative, you will end up with two imaginary solutions. Now, if the discriminant is equal to 0, that means you have one rational solution. And it is important to know that the one rational solution is also going to be your vertex. So when you solve using the quadratic formula for x, that is the x coordinate of the vertex, and the y coordinate will be 0. So that only occurs when the discriminant is equal to 0. If the discriminant is greater than 0, then it gets a little bit more complicated. Either it can be a perfect square like 4, 16, 9, 25, 49, etc., or not a perfect square. So remember, a perfect square is any number whose square root is also a whole number. So if the discriminant is a perfect square, you should expect two rational solutions. Now, remember, rational numbers are numbers that can be written as fractions. So any fraction, any whole number, any negative number, these are all rational solutions. So if the discriminant is greater than 0 and a perfect square, then you should expect 2 rational solutions. If the discriminant is positive, greater than 0, and not a perfect square, then you should expect 2 irrational solutions. Remember, irrational numbers are numbers who cannot be written as fractions, like the square root of 2, the square root of 7, and so on. Now, something to note, even though you should first try factoring, if you do not try to factor first and use the quadratic formula for all quadratic equations, if the discriminant is equal to 0 or greater than 0 in a perfect square, these are the discriminants that you would have for quadratics that are factorable. So if you could have factored it, you knew that it was a factorable quadratic if you end up with a discriminant that is 0 or a perfect square. Okay. Now, we also said that this is a key, it's pretty important to know that if you have 2 imaginary solutions, that means that if you have an imaginary solution, remember imaginary numbers are numbers with I, that its conjugate is also going to be a solution. That means, for example, if 1 plus I is a solution, then its conjugate, 1 minus I, would also be a solution. And this comes directly from the results of the quadratic formula. Now, also, if you have irrational solutions, so say for example you have a solution 2 minus root 3 as a solution, then its conjugate also is a solution. Okay, so if you have imaginary solutions, their conjugates are going to be solutions. If you have irrational solutions, their conjugates will be solutions. Rational solutions does not indicate that their conjugates have to be solutions. Only when you have imaginary or irrational solutions can you say that their conjugates would be solutions. So that's important to remember going forward, especially in this chapter, that when you have irrational or imaginary solutions, that their conjugates are also solutions to the equation. Okay, also last lecture we talked about the remainder theorem and the factor theorem. Just to remind you, the remainder theorem says that an equation evaluated at A is the same as the remainder of the polynomial g of x divided by x minus a. And the factor theorem says that if the remainder is 0, then we can say that x minus a is a factor of the polynomial. So just to show you guys, or to remind you guys how we did this, let's take, for example, a situation like this. Let's say I am going to give you a polynomial g of x equals 5x squared minus 6x minus 8. And I want you to evaluate g at -1. Now, yes, I can plug in -1 and solve, or I can use synthetic division. So remember, I can do -1 in the box in the upper left-hand corner. And then to the right of that box, I write the coefficients of my polynomial. And below the last coefficient, I put a box so that whatever that is in that box is the remainder. So remember how I do synthetic division. I bring the first number down the way it is, multiply it by -1, whatever number's in the box. And then I add -6 plus -5 is -11. -11 times -1 is 11. And then -8 plus 11 is 3. So that means g of at -1 is 3. Now, I want also, so basically that's what the remainder theorem says, that the function g of x evaluated at -1 is the same thing as me dividing -1 into g of x. Now, if my remainder was 0, then I would say -1 is a factor of the polynomial. Moreover, I would say x minus -1 or x plus 1, because minus and negative is positive, would be a factor. But it is not a factor because we have a remainder. Now, what if I said show that x minus 2 is a factor of this polynomial? So I want to show x minus 2 is a factor of g of x. So in order for x minus 2 to be a factor, then when I divide by 2, I should end up with a remainder of 0. So I do synthetic division. And I get a remainder of 0. That means that x minus 2 is a factor of g of x. Or another way of saying it, g of 2 is 0. Now, remember what this is. This is the coefficient of the coefficient. These are the coefficient of the quotient 1 degree less than my dividend. So my dividend was a quadratic. So the quotient is a linear term. So that means that is my quotient. Okay. So those are the two things we talked about last class. And if you need to review, just go ahead and do that. Main take-home points are basically, what is the quadratic formula? How do we use the quadratic formula? And when do we use the quadratic formula? What is the discriminant? What is the significance of the discriminant? And what does the remainder theorem and factor theorem imply? Now, I highly recommend that if you are not familiar or have a sketchy hold of this, that you do not proceed forward and you do some practice. So the question is, why are we doing all of this? So our main goal is to be able to graph a polynomial. So we know, based on the leading coefficient and the degree of the polynomial, the end behavior of the polynomial. So what happens at its end? And we can tell, based on the degree, the number of turning points in the polynomial, possible turning points. Now, in order to get an accurate graph, we need two more things. We need to know what the y-intercept is, or where the graph crosses the y-axis, and we need to know what the x-intercepts are. Now, remember, in a function, you will only have one y-intercept. And the y-intercept is usually your constant term. So for example, if I have a function f of x equals, say, 3x cubed plus 2x squared minus x plus 4, my y-intercept is simply the constant term. So in this case, 4. So the y-intercept is 0, 4. That means this graph will cross the y-axis at 0, 4. Now, the x-intercept is a little bit more involved. The x-intercept, remember, the synonyms for the x-intercept are solutions, roots, zeros, and factors. So finding the x-intercept is kind of complicated, and it's a lot more complicated than finding the y-intercept. In order to find the x-intercept, you have to set the equation equal to 0 and solve. Well, which is no problem if you have a quadratic, because we have means of solving a quadratic. We try to factor, and if we can't factor, we can always rely on the quadratic formula as a means of last resort. However, not all polynomials are quadratics. We have third degree polynomials, fourth degree polynomials, fifth degree polynomials, and so on and so forth. So what do we do? How do we find the zeros of these higher degree polynomials? And this is where this section comes in. Okay, this is where this section helps in figuring it out. Now, before we go forward, we need to talk about the fundamental theorem of algebra. Okay, so the fundamental theorem of algebra is pretty significant. And it says that if f of x is a polynomial of degree n, where n is greater than or equal to 1, so a linear polynomial or higher, then the equation f of x equals 0 has at least one complex root. Now, another way of saying that is the degree of the polynomial is equal to the number of complex zeros or complex roots. So remember from our discussion, complex numbers can be both imaginary and they can be real. And if they're real, they can be either rational or they can be irrational numbers. So what it says is that if you have a polynomial of, say, degree 4, or or a cubic, degree 3, that's the number of complex zeros that you have to have, or complex roots. That means, say, a fourth degree polynomial has 4 complex solutions. That means those 4 solutions can be either imaginary, rational, irrational, or a mixture of the 3. Okay. Now, same thing with degree 3. If we have a degree 3 polynomial, that means we have 3 solutions. Either they're imaginary, rational, irrational, or a mixture of the 3. Now remember what we talked about earlier about the quadratic formula. That if you have a complex solution, if you have an imaginary solution, a plus bi, then its conjugate, a minus bi, is also a solution. Okay. If you have an imaginary solution, then its conjugate is also a solution. So imaginary solutions come in pairs. Likewise, if you have irrational solutions like square root of 2, square root of 5, then its conjugate also is a solution. So just to reiterate, if you found that the solution is 1 plus 2i, then you know 1 minus 2i has to be a solution. If you find the solution is 3 plus the square root of 7, then 3 minus the square root of 7 must also be a solution. And this comes directly from the result of the quadratic formula. Now, if you have rational solutions, like fractions or whole numbers, then that's not the case. Its conjugate may or may not be a solution. But if your solutions are imaginary or irrational in nature, then those conjugates must also be a solution. So let's look into what the rational root theorem or the rational zero theorem says. That given a polynomial with integer coefficients, then all rational zeros must be of the form p over q, where p are the factors of the constant term, a sub 0, and q are the factors of the leading coefficient, a of n. So it says that if I have rational solutions for a polynomial, that doesn't say it must have it. It says if I have rational solutions, then they are the result of making fractions that are factors that are formed from the factors of the constant term divided by the factors of the leading coefficient. So, for example, let's take, for example, this situation. List all possible rational zeros of negative x to the fourth plus 3x squared plus 4. So it says that if this polynomial has zeros or roots or x-intercepts, then those x-intercepts must be of the form P over Q, where P is the factors of the constant term divided by factors of the leading coefficient, which in this case is -1. So factors of 4 include 1, 2, and 4. Factors of -1 are just 1. So the possibilities of P over Q can be positive or -1, positive or -2, positive or -4, because 1 over 1 is 1, 2 over 1 is 2, and 4 over 1 is 4. And then when we do the factors, so first what you want to do is write all of the possible fractions that can occur. So take every factor in the numerator and put it with every factor in the denominator. And then when you simplify the fractions, these are your possible solutions. Now, in addition, when you have the solutions, make sure you write positive and negative. So it can be +1 or -1, +2 or -2, +4 or -4. Okay, so let's look at checkpoint 1. List all possible rational zeros of x cubed plus 2x squared minus 5x minus 6. So P over Q, factors of the constant term, which is 6, over factors of the leading coefficient, which is 1. Factors of 6 are 1, 2, 3, and 6. Obviously, factors of 1 are just 1. Now you make all of your ratios. So you go 1 over 1, which is 1, 2 over 1, which is 2, 3 over 1, which is 3, and 6 over 1, which is 6. And before you're done, make all of those possible roots positive and negative. Okay, so look at the total number of possible solutions. You have 8. You have +1, +2, +3, +6, and you also have the negative variations, -1, -2, -3, -6. So again, it says that this theorem says that if f of x has a x-intercept or a solution, and they are rational, not saying they have to have any rational solutions, but if it has any rational solutions, then they are of the form either 1, 2, 3, and 6, or -1, -2, -3, -6. All right, I want you to try examples 2 and checkpoint 2. And I would like you to pause the video and see if you can do it yourself, and then we will walk through it. Unpause it when you have an answer. Okay, so let's walk through these. So if we have solutions to this polynomial, then the solutions are P over Q, which are factors of 2, which is my constant term, over factors of 15. So factors of 2 are 1 and 2. Factors of 15 are 1, 3, 5, and 15. So now I'll make ratios. So 1 over 1, 2 over 1, 1 over 3, 2 over 3, 1 over 5, 2 over 5, 1 over 15, 2 over 15. And then 1 over 1 is 1, plus or minus. 2 over 1 is 2, plus or minus 1/3, plus or minus 2/3, because we can't reduce them. Neither can we reduce 1/5, plus or minus 1/5, plus or minus 2/5, plus or minus 1/15, and plus or minus 2/15. So these are all the potential solutions, rational solutions of this polynomial. Saying that if it has solutions, not saying that it does, if it has rational solutions, not saying that it does, then they are either positive -1, positive -2, positive -1/3, positive -2/3, positive -1/5, positive -2/5, positive -1/15, and positive -2/15. So you have 16 potential solutions. Now remember what the fundamental theorem of algebra says, that since this is a degree 3 polynomial, that means you either can have rational, irrational, or imaginary solutions. You can have 3 complex solutions, but remember complex solutions are rational, irrational, or imaginary. So the way we look at it is say, okay, well, what's the possibility? We can have 3 rational solutions, or we can have 2 imaginary solutions, because remember, imaginary come in pair, and 1 rational, or we can have 2 irrational and 1 rational. Notice we can't have 2 imaginary and 2 irrational because that means we would need a degree 4 polynomial. So based off of this, using both the fundamental theorem of algebra and the knowledge of what we know, how the solutions come, whether they come in pairs or single, we can determine how many rational and potentially how many irrational or imaginary we may have. So if we have a rational solution, all of them have to be one of these, okay? Now, notice, these are all rational probabilities. This does not tell you that what your irrational or imaginary solutions are. It just says that if it's a rational solution, all rational solutions, potential rational solutions of this polynomial must be one of these 16 that we just discovered. Okay, so I want you guys, okay, so let's look at checkpoint 2. Okay, so the potential rational solutions are P over Q. Okay, so P are factors of 3. Over Q, which are factors of the leading coefficient, which is 4. So my factors of 3 are 1 and 3. And factors of 4 are 1, 2, and 4. Now, 1 over 1 is 1. 3 over 1 is 3. 1 over 2 is 1/2. 3 over 2 is 3/2. 1 over 4 is 1/4. 3 over 4 is 3/4. Remember, you have to do the positive and negative. So these are all the possible solutions, rational solutions of this polynomial. Now, remember, this is a degree 5 polynomial, so that means we have 5 complex roots. That means they can be rational, irrational, or imaginary in solution. And there's a whole host of possibilities. Okay, remember, imaginary and irrational come in pairs. Rationals can be single. So you can have 5 rational, 2 irrational, and 3 rational, 4 irrational, because remember they come in pairs, 1 rational, 2 imaginary, 3 rational, 4 imaginary, 1 rational, or even 2 imaginary, 2 irrational, because they both come in pair, and 1 rational. So these are the characteristics of the types of solutions. Now, this brings up a pretty important point. How do we determine from this pool of zeros what are our potential zeros? Well, remember what the factor theorem said. The factor theorem said that if I do synthetic division and get a remainder of 0, then that number is a factor of the polynomial. So let's take, for example, example 3. Find all the zeros of this polynomial. So all the potential zeros will be in the form, all the potential rational zeros will be of the form P over Q, where P is the factors of 6, which is 1, 2, 3, and 6, because 6 is my constant term, divided by factors of the leading coefficient, which is 1. So potentials are positive and negative 1, positive and negative 2, positive and negative 3, and positive or negative 6. So remember, it's a degree 3 polynomial. So I have a potentiality of 3 rational, or 2 imaginary, and 1 rational, and 2 irrational, and 1 rational. So got a question. Why can't I have 2 imaginary and 2 irrationals? Something to think about. Well, if you think about it, if I have 2 irrationals and 2 imaginaries, because they come in pairs, they have to come in twos, then that means I have 4 solutions, and that's larger than the degree of my polynomial. Now, how do I determine which one of these solutions is my solutions for my polynomial? Well, synthetic division. And basically what you have to do is trial and error. And there's no pretty way of doing it. So you start off with 1. Let's start off with 1 and do synthetic division with 1. So remember, we write the coefficients of my polynomial, making sure that it's in descending order of power and all zeros are and all powers are represented. So 1 times 1 is 1, 3 times 2 plus 1 is 3, 3 times 1 is 3, negative 5 plus 3 is negative 2, negative 2 times 1 is negative 2, and negative 6 plus negative 2 is negative 8. So notice my remainder here is negative 8. It's not 0. So 1 cannot be a solution to this polynomial. So let's try again. We have to do, so 1 is not a solution. So we go back to the drawing board. Now it could be negative 1. So let's try negative 1. 1 times negative 1 is negative 1. 2 plus negative 1 is 1. 1 times negative 1 is negative 1. Negative 5 plus negative 1 is negative 6. Negative 6 times negative 1 is 6. And got 0. So negative 1 is a factor. So if negative 1 is a factor, that means x minus negative 1, or what is minus a negative? X plus 1 is a factor. Now, remember, we need to potentially find 2 more. We found 1 factor, or 1 0. Now we want to find all the other factors. Now, you can go back to your pool and do it again. Or you can say, look, this is a quotient that is 1 degree less than my dividend. My dividend was a cubic. That means my quotient is a quadratic. So that means the quotient is x squared plus x minus 6. Now, I don't need to do synthetic division and trial and error to find factors of x squared plus x minus 6. I can do other things. I can either use the quadratic formula to find the factors, or I can use factoring to find the factors. Now, whatever are the factors of x squared plus x minus 6 are also the factors of my original polynomial. So whatever I find to be the factors of this quotient are also factors of f of x. So how can I find the factors of x squared plus x minus 6? Now, yes, you can use the quadratic formula, but I remember I told you to do this as a means of last resort. Try factoring first. Can x squared plus x minus 6 be factored? Well, it can. It can be factored into x plus 3 times x minus 2 equals 0. Then that means we set x plus 3 equal to 0 and x minus 2 equal to 0 and solve and get x equals negative 3 and x equals 2. Okay. So my factors of x cubed plus 2x squared minus 5x plus 6, or my solutions, are -1, the solution that we found. Let me do this in another colorway so to distinguish between all my work. So -1, the one that we used to find with synthetic division, and -3 and 2. So these are my zeros. And notice all of these three are rational numbers. They're whole numbers, they're rational numbers. And they're all in the pool of potential rational solutions that I created in the beginning of the problem. And notice I have 3 zeros. That means I have 3 rational solutions. So this is a lot, I understand. And you probably are like, whoa, this is mind-blowing. But trust me, with a little practice, it comes. Just take it a step at a time. And there are ways of making it easier. So let's walk through one more. Find all the zeros of x cubed plus 8x squared plus 11x minus 20. So the first thing you're going to do is create your list of potential zeros. So they got to be of the form P over Q, where P is the factors of -20, over the factors of the leading coefficient, in which case this is 1. So the factors of 20 are 1, 2, 4, 5, 10, and 20. And factors of 1 are 1. So my potential factors are positive and -1, positive and -2, positive and -4, positive and -5, positive and -10, positive and -20. Now, unfortunately, there's no other way of figuring out what are your zeros besides doing synthetic division. So set up my synthetic division table, write out my coefficients, making sure that the original polynomial is in descending order of power and all powers are represented. Now, let's try, I don't know, let's try -2. So let's see what happens. Okay. 1 times -2 is -2. 8 plus -2 is 6. 6 times -2 is -12. -12 plus 11 is -1. -1 times -2 is 2. It's -18. So -2 cannot work because it doesn't have a 0 as a remainder. So let's try +2. Okay. 1 times 2 is 2. 8 plus 2 is 10. 10 times 2 is 20. 11 plus 20 is 31. 31 times 2 is 62. And that gives me 42. Again, +2, as we see, doesn't work. So let's see here. Let's try -1. Let's see. First coefficient comes down. 1 times -1 is -1. 8 plus -1 is 7. 7 times -1 is -7. -7 plus 11 is 4. 4 times -1 is -4. It's -24. So -1 doesn't work. Let's try -5. 1 times -5 is -5. 8 plus -5 is 3. 3 times -5 is -15. 11 plus -15 is -4. -4 times -5 is 20. So -20 plus 20 is 0. So that means -5 is an acceptable factor. So if -5 is a 0, that means x minus -5 or x plus 5 is a factor. Now, again, we're looking for all zeros. So remember, this is a third degree polynomial. That means we have potentially 2 more rational zeros. Or it's possible we have a pair of imaginary or irrational zeros, but we don't know that yet. So we can again go back to the drawing board and try all the other potential zeros that we have in our pool, or we can say, wait a minute, this is a degree 3. So that means my quotient is a degree 2 or quadratic. So x squared plus 3x minus 4. And whatever are the factors of x squared plus 3x minus 4 are also factors of my original polynomial. And thank God we can actually factor these, okay? So remember, how do we factor? We find 2 numbers that multiply to give me -4, but combine to give me, or add to give me +3. That includes x plus 4, x minus 1. So we set each binomial equal to 0 and solve, and we get x equals -4 and x equals 1. So my zeros, or my solutions, are x equals -5, -4, and 1. So we have 3 rational solutions. I know it's complicated, I know it's a lot, but this is just the best way we know how so far. Now, there is a little trick that you can use, and you can use your graphing utility to help you with this. So remember, we talked about multiplicity, or the number of times the solution is repeated, okay? So if we have a multiplicity of 2, that means the solution is repeated twice. And remember what happens with multiplicity, that if I have an even multiplicity, the graph touches at that value of x and goes the other way. And if it is an odd multiplicity, at that value of x, the graph crosses it. So let's take, for example, this 4th degree polynomial. So what are our potential outcomes? We can have 4 rational. We can have 2 irrational and 2 rational. We can have 4 irrational, and no rational. We can have 2 imaginary and 2 rational solutions. We can have 4 imaginary solutions. Remember, imaginary and irrational come in pairs. And no rational. And we can also have 2 irrational and 2 imaginary. Now, something to be, so look at all the potential types of solutions we can have. We can have 6 potential outcomes between rational, irrational, and imaginary. In addition, some of those rational solutions can have an even multiplicity. That means they're repeated 2 times or 4 times. So all 4 rationals might be the same number with a multiplicity of 4, or they can be 2 solutions with multiplicity 2. And there's a whole other thing. So like even with the 2 rational, this might be 2 separate rationals, or it can be 1 solution with a multiplicity of 2. So that makes things even more complicated. So how in the heck do we make our life a little bit more manageable? Well, this is where the graphing utility comes in, your graphing calculator. You graph it in your graphing calculator, and you see on the graphing calculator where it crosses the x-axis. Where it crosses the x-axis is where the zeros of the polynomial are. Now, the way it touches or crosses the x-axis tells you the multiplicity. So let's take, for example, the problem here and look at the graph of this polynomial, okay? So you look at the graph of this polynomial and you see that at 2, right here, it doesn't cross. It touches and it goes back up. Well, what does that mean? Well, that means that at 2, x equals 2 has an even multiplicity. So it either has a multiplicity of 2 or 4. So that we already, by looking at the graphing calculator, we can tell, number 1, what are my zeros? And number 2, we can tell what is the multiplicity of those zeros and how many times they're repeated. If they cross, if the graph crosses the x-axis at that value, that means it's an odd multiplicity. If it touches, that means it is an even multiplicity. So right here, we know it's an even multiplicity. So it's either the solution x equals 2 is repeated twice or 4 times. So we know 2 is a solution. So we know that when we do synthetic division with it, we should get a remainder of 0. So let's do synthetic division. Now you see the mistake I made? I purposely did this. Okay, remember the powers must be represented. So what power did I not have? See, I didn't have the cubic power. So remember to put that there. So with synthetic division, we got a remainder of 0, and that's what we expected. Now, the problem is we just can't take this, write it as a polynomial, and factor it. Well, why? Because my original polynomial was a 4th degree. So that means that this is a 3rd degree. And we don't know how to factor 3rd degrees. But we know that this solution x equals 2 is repeated twice. So if 2 is a factor of the original polynomial, it is also a factor of this polynomial. So we can do it again. So now, look, we got a remainder of 0. So that means the solution x equals 2 is repeated twice. Now, what is the degree of this polynomial that is in my quotient? Well, now, since my initial, before my synthetic, it was a degree 3, now it is a degree 2. And now that it's a degree 2, we can write it as a quadratic and solve it. Now, notice x squared plus 4x plus 6 is a non-factorable polynomial. Okay, there's no factors of 6 that add to give me 4. So how do we solve a non-factorable polynomial? Well, we use the quadratic formula. So we first calculate my discriminant. A is 1, B is 4, C is 6. So we calculate it. 16, which is b squared, or 16 minus 4 times A times C. So the discriminant is -8. 16 minus 24, which is -8. So the discriminant is -8. Well, what does that tell me? That tells me that I have two imaginary solutions. So let me erase this. So we found the discriminant to be -8. So x equals -b plus or minus the square root of the discriminant over 2a. So -b, which in this case is -4, plus or minus the square root of -8 over 2 times 1, which is 2. So -8 can be rewritten as -1 times 4 times 2. Remember, when we pull out -1, it becomes I. When we pull out 4, it becomes 2. And this 2 stays underneath the radical. So this becomes -4 plus or minus 2I root 2 over 2. Now, we want to clean up the fraction to see if there's any common factor in the numerator. And the common factor is 2. When we pull out -2, we get plus or minus I root 2 divided by 2. The 2's cancel, and that gives me solutions of -2 plus 2I and -2 minus 2I. So my zeros are x equals -2 plus 2I, -2 minus 2I, and x equals 2 with a multiplicity of 2. Now, I know this seems like a lot, but let me go through it one more time. The first thing we did was say we graphed it, and we saw that it crossed the x-axis, it touched the x-axis at 2. Since it touched and didn't cross, we know it had a multiplicity of either 2 or 4. So we did synthetic division with a known 0, x equals 2, not once but twice. So we started off with a 4th degree polynomial. with the first synthetic division using 2, no, that's a known factor, we ended up with a quotient that's degree 3. We couldn't factor a degree 3 polynomial, so since the multiplicity means that the answer is repeated twice, we again did synthetic division with the degree 3 polynomial, and we reduced that quotient down to a degree 2. Once we got a degree 2 polynomial, we did the quadratic formula because we couldn't factor it. And when we calculated the discriminant, we got a negative number, meaning that we had 2 imaginary solutions. And we knew we were going to get 2 imaginary solutions. And then when we finished it up, we found that the 2 imaginary solutions are -2 plus 2i and -2 minus 2i. As I said earlier, they're both conjugates of each other. So my total zeros are -2 plus 2i, -2 minus 2i, and x equals 2 repeated twice or with a multiplicity of 2. So I want you guys to try this guy right here, x to the 4th minus 6x cubed plus 22x squared minus 30x plus 13. And next time we're going to pick up from this checkpoint. We're going to solve this, and then we're going to talk about the Descartes rule of signs and the linear factorization theorem. Thank you.